membrane layers, that this thing is not going to speed up. Oh, because the calcium that's freed from the sarcoplasmic reticulum is mostly concentrated in the cytosol, not in, it takes a while for it to build up inside the mitochondria. For all these reasons, accelerating your mitochondria is slower. Right. The work starts as soon as the contraction starts, and you better cover that work or you're done. However, the mitochondria won't be ready to cover it, and so this is one of the reasons we have all these intermediate steps like phosphocreatine. Phosphocreatine is like a backup battery. I finally got the right analogy. Don't you guys carry little charge units that will bump up the charge on your cell phone or laptop? That's phosphocreatine. It's a short-term battery for emergency resuscitation. Then we saw last time a second layer of defense for ATP is you can use these glycogen granules that are out here in the cytosol and partially break them down with a 10-enzyme chain ending in lactate. Oh, great questions from last time. Several of you came up afterwards and said, now I get it. Last lecture you put up a slide that said you got 3 ATP. Did anyone have that experience? Because that was driving me crazy. People were saying, I was seeing you said you got 3 ATP from glucose in the cytosol. No, we were taught you get 2. And just to realize, your basic biochemistry professors are not wrong. They're absolutely right. But they were referring to, say, a piece of blood glucose that is delivered to the brain that has essentially no glycogen storage. There's nowhere to put it inside your skull. Does that make sense? And so most a piece of blood glucose that goes to a skin cells don't care about having a glycogen store. I said 95% of the body's glycogen is in muscle. So for every other cell population, that value of 2, that you invest 2 ATP, you get 4 back out from a glucose, and therefore your net harvest of ATP is 2. Well, that's up by 50% in a muscle because of this ability to pre-store glycogen, which are phosphorylated glucoses. So you get 3. Bonus. So let's talk about today what we do after that initial kind of cytosolic stimulation. So we talked about you can short-term resuscitate with phosphocreatine or adenylate kinase. You can break glycogen down to lactate. We don't have a to lactate as another sort of short-term solution. Then as the mitochondria starts to adapt and come up to speed, you can get, for instance, if you get 3 ATPs from lactic acid from glycogen, you can get it for 30, potentially, if you can pull either the lactic acid or the pyruvate into the mitochondria and finish harvesting the energy in its carbon-carbon bonds. So let's do that. 2, of course. 1 glucose leads to 2 lactic acids or 2 pyruvate, and if you get those 2 in here, you can get a bunch more energy. So today we're going to talk about how do we derive mitochondrial oxidation and get energy from glucose, and then I think on Monday we finish by talking about fatty acids. By the way, I have too many slides today, and so once again, rather than rush, we'll quit when we get somewhere and finish today's lecture on Monday. You need to rest. So, we'll talk a little bit about oxidative metabolism. Remember, we're doing this because oxygen is the prime acceptor of electrons and protons. Oxygen gets reduced into water in the electron transport chain, which we'll talk about today. And so oxidative metabolism is really kind of a summary. As long as the creature is stable, if you measure their oxygen consumption, you're kind of getting a short-term signature of their entire metabolic. That's what we're measuring outcome, because most of us, if we're not in a transition into exercise or not in the midst of dying, most of us are paying for everything we do with oxidative phosphorylation of ATP. Huge amounts of ATP, like I just said, 30 out of a glucose if you can get it into the mitochondria, only 3 if you do it in cytosol. Unfortunately, because the enzyme chain is about 3 times longer, there's at least 30 enzymes or steps in oxidative phosphorylation glucose, or oxidative respiration glucose, and so it takes longer. So mitochondria are not fast, but good grief, they can go forever. They're the energizer bunny of organelles. Endurance events. All 3 macronutrients conserve, although protein is reserved. You don't want to eat your body unless you must. So today we're going to talk about this central pathway, glycolysis to pyruvic acid, and we get an entry level into the mitochondria is right about there. That would be pyruvic dehydrogenase that pulls the pyruvic acid out of the cytosol and drops it off in the mitochondria as acetyl-CoA. How many people have never heard of this? The TCA cycle, Krebs cycle. Ever heard of mitochondria? Good, it's a good sign. So let's think about steps. We said there's a prep step. In many ways, you can think about the cytosolic reduction. It's nice that it provides ATP and is a short-term backup, but it's a prep step to get the 6-carbon hexose down to something that can actually enter the mitochondria. Right? We'll see on Monday when we talk about fats. Fats create an even bigger problem because basically what you want inside the mitochondria are 2-carbon acetyl-CoAs. Well, fats arrive 30 carbons long sometimes, and so boy, the prep step for fats is going to be far more protracted, you'll see. The PDH, this is your gateway reaction. This is the entry of substrate. This is the equivalent of hexokinase for glucose getting into the cell. The pyruvate dehydrogenase reaction is the step that pulls pyruvate through the cell membrane into the mitochondria itself. Then we go through the TCA or Krebs cycle, a 10 enzyme chain, and then we do electron transport with the reduced coenzymes that we have generated up here. Familiar? Okay. I don't want to bore you, but I want to make sure that you remember all this. Oh, we're going to have an interesting, this is interesting, good for them for having put it here. Do you remember that if we don't make pyruvate, if we don't make lactate, if we don't take this to its step to lactate and regenerate NAD, we are gradually, the more glucose we're breaking down, we are building up NADH in the cytosol, which is ultimately a losing proposition. You need the naked or oxidized NAD to continue the process. Make sense? Remember that? So, sort of a sidestep, and I don't know whether it's in the next couple of slides. We need to think about how, if we're not making lactate, if we're at rest, how do we clear these NADHs out of the cytosol and into the mitochondria? Right? There's several ways to do that. Oh, good. It is the next slide. So we have shuttles. The mitochondrial membrane is impermeable to this molecule. And so you actually have to transport it across in other, you have to do molecular exchanges. And so if we could somehow get these reducing equivalents of the electrons and the proton onto something else, and then get it into the mitochondria, see, in the cytosol, this NADH is actually gumming up the works. You can't have more pyruvate if that starts to build up. On the other hand, if you can get it into the mitochondria, that NADH is redeemable for, I'm trying to remember, 2.5 ATP? Yeah. So we have 2 shuttles that do this. Here's the word shuttle. These shuttles are intracellular. They're from the cytosol into the mitochondria. We're going to go through each one. Let's do glycerol phosphate because it's the easier one. Oh, and here's your stoichiometry for reduced coenzymes NADH. Will give you 2.5 ATP if you can get it to the electron transport chain. FADH2, because it enters later in the electron transport proteins, only gets you 1.5. Okay? So we have 2 different shuttles I want to do the easy one first, because this, once again, is one of the hardest of this lecture. This is the hardest concept. Has anyone talked to you about these before? Familiar at all? So, again, why have they not, if that's the inner mitochondrial membrane, why is this not squiggly? Why is it not crispy? Okay. No one knows how to make a figure. Notice that if you have, this is the step in glycolysis where G through T shifts, absorbs its second phosphate, and in the course of that reduces an NAD to an NADH. How do we get that in? Well, since it's called the glycerol phosphate shuttle, it might be useful to remember that glycerol phosphate will accept the hydrogens and electrons, and that on the inner mitochondrial membrane, there's a protein that's basically acting as a shuttle. It is removing the reduced energy that came along from the NADH in the cytosol and passing it on to reducing an FAD, a flavoactinoate. See that? So can someone tell me, because you ought to have an objection right away, what is the drawback of turning an NADH into an FADH2? You just tossed away an ATP in the mitochondria. So it's okay. Remember, all of these are evolved systems that are just sloppy goo and a lot of proteins gooing in a bunch of water. There is no perfection in this life. So maybe it'll help you remember that this shuttle is most present in fast twitch fibers. So we're starting to develop an idea. Remember, the primary thing of fast twitch fibers is they just have a fast ATPase. That's how they get their name on their myosin head. But you'll see as we get to fiber type next week, there's a lot of other little characteristics. They're sort of like, fiber types are sort of like you and your siblings if you have brothers and sisters. You know how there's certain similarities. You know, everyone in our family plays the fiddle, but there are differences. Well, you're going to learn that fast twitch fibers are really all about getting their energy from the cytosol. I'm not saying they don't have mitochondria. They do, and they use those mitochondria to cover their resting needs. But if you ask a fast twitch fiber to make contractions, it's mostly going to make lactate. And so, to some extent, fast twitch fibers don't care about reduced coenzymes. I don't know how else to say that. It's more important to get the NADH out of the cytosol than to have a really highly redeemable, efficient process into the mitochondria. They just don't care about mitochondrial ATP production as funding their force generation. So maybe that'll help you remember that. Okay? Alpha glycerol phosphate shuttle, fast twitch fibers. You get a step down in the energy of the reduced coenzyme. So by contrast, you can deduce that the malate aspartate shuttle must be used more often in slow twitch fiber. And notice that this one is actually going to, again, why can't the inner membrane be wiggly? Why can't there be goo in the matrix? I don't understand. Anyway, I have a much more visual appraisal than most people apparently. Or at least have this swing around like that so you can tell this is a contained space of mitochondria. Notice you're getting NADH made at the same step in the cytosol, and you're coming out with NADH at the end. So this clearly preserves all the redox potential and gets it into the mitochondria, but you won't like it because there's more steps. So let's see what happens. The NADH, apparently, if you reduce oxaloacetyl-CoA, it becomes a malate, and malate can get in through one of those transporters, probably one of those monocarboxylic acid transporters. So malate is permeable, unlike this, which bounces off the inner membrane. Malate will shuttle in. Once the malate shuttles in, watch what happens, because this is quite useful. It can reduce NADH. An oxidized malate is an acetyl. Are these things useful in the inside the cell? Yeah, this is your terminal step of the Krebs cycle, and all you have to do is plug an acetyl-CoA onto that, and you're on your way to citrate in another round. So this is hella useful in here. And you've just generated 2.5 ATP. Yes, sir?
Where does the original NAD come from?
Oh, very good. It comes from the when this G3P step yoke, right after the 6 carbon hexose is broken into 2 carbons, into 2 3-carbon moieties in glycolysis, each one with a phosphate as indicated by my pinkies. You need to get a second phosphate onto them before you can start yielding ATP. This step here puts a second phosphate, bisphosphoglyceraldehyde or whatever it is, bisphosphone. And apparently in the doing of that, this thing is very high energy. There's some energy left over and you're able to reduce an NAD as a cofactor.
I was talking about the one inside the mitochondria.
Oh, where did this come from?
Yeah.
This come from. This came from when you finish redeeming your reduced NADH in the electron transport. Remember, all the hydrogen ions and electrons flow across the 4 proteins of the electron transport chain. And so a end product in electron transport is naked NAD. That's where it's coming from. Remember, they're all just wandering around in there. Okay. Apparently, we're going to say pause a little bit and talk about the mitochondria in vigor. The mitochondria primarily has 2 primary metabolic pathways. The Krebs cycle or tricarboxylic acid cycle, and then it has the electron transport chain. Fat that is properly prepped can feed acetyl-CoA into the Krebs cycle, as can glucose. Proteins will usually be entered as though they were glucose. They'll be prepared and deaminated, and protein amino acids will enter as 2 carbon fragments, just like the mitochondrial respiration is tightly controlled, and what controls how quickly you're respirating is how quickly ATP is being used, and we'll see that in a moment. So it's very much a demand system. It's the disappearance of ATP that's driving how quickly you regenerate it. So we talked about where mitochondria are. Mitochondria are where energy use occurs. So there's some below the sarcolemma, and there's many intrafibrillar, running the whole length of the muscle cell outside of it. The outer lipid is pretty freely permeable. Almost all ions, when calcium gets in, it freely gets through the first layer. The stopping step is the inner membrane blocks most ions, and there's a pretty high electrochemical gradient because the intramembranous space is pretty hellishly low pH. So getting into the matrix is the hard step, and a lot of times there are specific transporters that do that. Remember the folding of the cristae, I often call mitochondria wrinkle beams. If you ever saw me talking about the wrinkle beams, I just am not taking the time to talk about mitochondria. Say the whole word. The inner membrane is also heavily crystalline, just like our cerebral cortex, which of course is a way to enhance surface area. Since the vast majority of the, so the actual, I can make words, the electron transport proteins are all studded on the inner membrane. PDH, many of the import and export, the monocarboxylic acid transporter, the pyruvate dehydrogenase, these are all membrane bound. And then these little dots here are representing the enzymes of the TCA cycle, which are basically suspended in the inner goo of the mitochondria. You guys are all familiar with the concept that the eukaryotic cell probably invited or ingested a free-living thing that looked a lot like a mitochondria in the ancient past, probably around, I can't remember when eukaryote, probably around 400 million years ago. And that is part of the reason why then that this thing has its own mitochondrial DNA. And so these things do undergo a kind of a mitotic equivalent, that they carry their own DNA. They can make, in a single mitochondrion, express more of these proteins as dictated by need in adaptation, and they can undergo reproduction and create more total mitochondria. Is that all familiar? So let's do the Krebs cycle. Matrix. Oxidation of carbohydrates. And you try to create reduced NAD. Krebs cycle. Acetyl-CoA, there's your entry. So we need to get our pyruvate to be acetyl-CoA, and that leads us to our next enzyme, remember that each glucose makes 2 pyruvates. And so each glucose makes 2 turns of the Krebs cycle. Pyruvate and lactate both can enter, although lactate will have to be flipped back to pyruvate, but that's no problem. It makes an additional NADH inside the mitochondria. So if you've imported lactate to your mitochondria, good for you. You're ahead by 2.5 ATP. All right? So let's do this step first. Remember, pyruvate has how many carbons? Acetyl-CoA has, there you go. So remember that in entering the inner membrane, pyruvate loses extra first CO2 production, and that creates acetyl-CoA that can begin to swing around the GCSA. So this is what I want to get to. So think of pyruvate dehydrogenase as kind of the gatekeeper for the aerobic use of glucose. We'll see in a moment how it's activated. Remember that PDH and LDH are somewhat in competition. What causes the early buildup of lactate at the beginning of a workload to stop is when PDH becomes sufficiently allosterically activated to outcompete lactate dehydrogenase, and most of the foreign pyruvate goes into the mitochondria. So here's pyruvate dehydrogenase. Oh, yeah. Here's pyruvate dehydrogenase. Oh, sorry, wait, stop, bad. Here's pyruvate dehydrogenase. Here's its inactive form, here's its active form. Just like with glycogen phosphorylase, the enzyme is either off or on. But it has most of the regulation is placed onto kinase phosphatase pair that are regulatory enzymes. These are the turners on and off. And so notice, let's see if we can figure this out. As pyruvate begins to arrive in through the outer membrane, it has an inhibitory effect on the pyruvate dehydrogenase kinase. So you stop phosphorylating your pyruvate dehydrogenase. That's the inactive form. So it's kind of the reverse. And phosphorylation can either activate or inhibit an enzyme covalently. So here we have a situation where if you cease to phosphorylate, you actually default into the most active form. Got it? And what will do that? The presence of calcium coming into the intermembranous space, the presence of pyruvate. Well, both of these are exercise phenomena. Let's not talk about these, but yolk, wherever you are, we were talking about turning off. Here are 2 more ways to turn off a mitochondria. When you start to build up some excess energy state, then it's like, well, why bother to import more energy from the cytosol if we're already fully energized? Does that make sense? Sir, ma'am. Sir, ma'am.
Did you say the pyruvate inactive or active?
Well, this is your regulatory molecule, and the regulatory molecule is set up to inactivate PDH. And so it's that situation where you have an inhibitor of an inhibitor. Sorry to say that, but a better way to say it might be that when these are present, PDH becomes disinhibited. It's like it's had 2 martinis and is now willing to dance on it. So. All right. And what you just asked is written right here because I had exactly the same confusion. All right. So here's your TCA cycle, which you've all met before. Here's our acetyl-CoA. So up here would be PDH on the inner membrane. It's just passed this through. And we've got a 2-carbon moiety with CoA group. 2 carbons plus 4 carbons. Watch how sophisticated I am. 2 carbons and 4 carbons, when stuck together, make 6 carbons. I can do it. And this is citrate. Yes, citrate synthase is the name of this first entry level. And you begin to go through several enzyme steps. Remember, we lost 1 carbon dioxide up here. We're going to lose 2 more. There's a carbon dioxide coming off of this chain. 1, 2, 3, 4, 5, 6. See if it worked. 1, 2, 3, 4, 5. I can do simple arithmetic. One of the reasons I'm trying to point out something is where is the energy that's making these reduced enzymes coming from? It's in the carbon-carbon bonds. And so anytime you see a CO2 coming off, very soon after that, you're going to get an either co-generated, you're going to get a reduced coenzyme, or it's going to come downstream from one of those. But whenever you snap the carbon-carbon bond to make CO2, whenever you decarboxylate, right after that, you're going to harvest energy. Okay? So let's go around. These first steps are sort of getting the high energy state set up. By the time you get to isocitrate, I think this is your rate limiting step. Isocitrate dehydrogenase, I could be wrong, we'll see in a moment. But this is your rate limiting step. You've got the highest energy system, and you will decarboxylate again, get one reduced coenzyme, then watch you get another decarboxylation step and another reduced coenzyme. You get a direct, this would be called substrate level phosphorylation. You actually turn a guanine diphosphate into a guanine triphosphate. So that's the equivalent of making 1 ATP without using the electron transport chain. So you're getting, boom, what is that? 2.55, 6 ATP are being generated from that very high energy. 6, another 1.5, 7.5 have come off, and I think we get any more energy. Oh, in our last step, as we take malate to the oxidized form, oxaloacetic acetate, the reducing equivalents come off malate. That's part of that shuttle, and get one more. It's another 2.5 on a 7.5 would make 8, would make 9, and then this 1. So we got 10 total ATPs are potentially redeemable if we can now get these NADHs and FADH2s into the electron transport chain. Remember, if that was somehow shut down, this is one of the problems with cyanide poisoning. Cyanide poisoning binds onto the electron transport protein, one of them, and shuts down your ability to redeem. So one of the reasons you'll die when you take your cyanide, don't take your cyanide, is you'll only be getting 2 ATP in the cytosol and 1 GTP compared to what you would have got if you had had a functioning electron transport. Is this all right? Make sense? You remember all this? Good. Oh, look, I put stars. Good for me. Anytime something is either decarboxylating or yielding energy, I seem to put a star on it. Good for me. So, what controls this? Doak and I this morning had a nice little chat about what turns on a mitochondrial porn. What turns on a mitochondria, and then how do you turn it off, right? These are our 2 interests in this class, is what really gets them going. Notice, once again, this is actually a adenylate charge, and notice that dropping adenylate charge stimulates citrate synthase. This is your rate limiting step, and look, calcium stimulates both of these 2 energy harvesting steps. So once again, byproducts of contraction. What are byproducts of contraction? Contractions don't start until calcium is present, and contractions by their very nature use up ATP. All make sense? Okay. Calcium. Again, it takes calcium longer to get through the double membrane barrier of the mitochondria, and that's part of this time lag between the cytosolic energy production and the mitochondria. All right. You can read that on your own. I think we've covered it pretty well, and I can tell by the glaze in your eyes you've heard this story before. Yeah? So let's talk about the electron transport chain. The electron transport chain is bound in the inner matrix. Oh look, I didn't even know there were calcium porters. Look, there appear to be calcium porters, so to actually get the calcium, remember this is mostly ion impermeable, so this is another reason the calcium is taking longer, is it's actually having to be transported on a specific protein. Didn't know that. So bound also into the inner membrane are a number of proteins that are now called 1, 2, 3, 4. We used to call them cytochromes, is the old name for them. The reduced coenzyme that was generated here in the goo of the matrix, these reduced coenzymes begin to cycle back this answers someone's question. Ryan, was it your question? Oh, your question. The reduced coenzymes that you've generated, again, you need naked coenzymes for the TCA cycle to keep going. And so the protons, that's not proton, the electrons and the protons get shuffled onto these proteins. The electrons skitter along across the protein surfaces, and the protons wind up pumped into the intramembranous space. So the intramembranous space has a hugely high concentration of protons. It has a very low pH. Is that okay? The business end then, oh, by the way, why do FADH and NAD have slightly different energies? I think the next slide may show it better. But NADH starts at the very first complex. FAD, I think, enters over here, and so it misses a couple of proton pumpings to the tune of, I think it's four protons make one ATP, so it misses 4 protons being pumped, and as a result, FAD gives you slightly less energy because it enters late, comes late to the party. Okay? Okay. I think I have 3 slides that all say the same thing here, so we'll see what they do, but there's a thing called oxidative phosphorylated coupling. What makes the electrotransport chain go? And this is, I love this. It's not allosterism. It's not hormones. It's simple substrate product balance. It's beautiful. And this has the highly technical name oxidative phosphorylated coupling. It's just, I remember people said that to me over and over all the way through medical school before I finally got what they were trying to tell me. They're saying that the amount of oxygen consumed in the electron transport chain is directly related to how low the phosphate charge of the cell is. Basically, if you use up energy, you have available more inorganic phosphate, more ADP, more naked creatine, and the whole system goes faster. So it's very much a substrate product driven system, automatic. So now we can look at a few other things. Here's FAD entering on the second complex, good for me for remembering. Therefore, it lists the pumping of 4 protons. It is these protons that actually are redeemed when we get over to, we don't have ATP synthase, but in a moment you'll see that 4 protons are redeemable through this very cool molecular engine where protons attach. The motive force, the reduction force that this chemical gradient creates allows one to take an ADP and join one additional phosphate to it and releases an ATP. And I'll try to play this as we finish. It's a video. I think you can read about all of this. Complex 1, complex 2, complex 3, complex 4. And then here's your ATP synthase. All of these are, I think, ATP synthase. Let's skip, let me see what we got next. So we still have 15 minutes so we can relax. The ATP, this is going to, adenosine triphosphate is kind of a big molecule, and it does not permeate that inner membrane. So you've got this situation, sort of like the same problem that the muscle made all its force inside the cell membrane, because that's where it could have calcium and ATP and all. But where does the force actually need to get? Out. Well, same problem in this organelle. You've made all your ATP in here. Where's the ATP all being used up during contraction? Ah, crap. And this is membrane impermeable. So the way that you actually get, oh, by the way, so the adenosines inside a mitochondrion are completely a separate population from these adenosines. They're totally different. The high energy phosphates are shared. That's what's passed. And so what happens is, in here, there is a boundary level, mitochondrial creatine kinase. where creatine, free creatine from out here in the cell, which we saw was created by contraction, you start to use up your phosphate, the free creatines, they drift in through the outer membrane. This enzyme catalyzes the ATP into creatine phosphate and ADP. This is totally cool because the ADP keeps the electron transport chain functioning, and it supplies to the cytosol the exact thing it needs to continue the contraction. It's one of the reasons why in these pictures I keep showing you, the sarcomere is butt right up against the mitochondria. Yeah, they're swapping spit like crazy. It's okay? Cyanide bad. Yeah, cyanide. I know stuff. I'm a physician. Cyanide, you could go look it up, but I'm pretty sure cyanide actually blocks complex 4, which is where the oxygen is processed, and that's why cyanide results in such rapid death. All right. Oh, and that's phosphorylative, this big term that everyone whips out as though it's completely understandable. It's not. What it's telling you is the rate of ATP formation inside of mitochondria, how fast the ETS is going, is very tightly connected to how quickly ADP is appearing inside the mitochondria. That's another way of saying how quickly creatine phosphate is being depleted out of the cytosol. Is that okay? All right. Good for you. You're so quiet. Ooh, I think we're going to get to end with a video. I'm in favor of that. So, let's go through what we've just said. We're going to run through all the way from a molecule of glucose entering the cell and try to get our energy balances. By the way, there's certain things I don't care about. I don't care about delta Gs. I don't care about the molecular chemistry of how the bonds move around. I do care about what speeds the system up, what slows the system down, what determines flow at branch points, and I care about your total energy balance. So let's start with cytosolic glycolysis. Why are there two different numbers here for ATP? It'll be a quiz.
Blood glucose.
Yeah, we imported the glucose from the bloodstream. We had to phosphorylate it with hexokinase, and so it added 1 to our investment step. If we come from glycogen, we get 3, and so clearly the way this is written is all screwed up. They've got the parentheses mismatched. That 3 is from glycogen, 2 is from glucose. In terms of, then the oxidation of cytoplasmic NADH. Oh, this is very interesting. So this is NADH. This is a review of the whole lecture. I didn't know that. I just work here. So the generated NADH in the cytosol. Remember from the 3PG step, G3P step, you generate NADH. And you get it into the mitochondria. So why are there 2 numbers here?
Is that based on how activated the enzyme to get it in is?
Getting really close. It has to do with what gets it in? Through the shuttle. And so if you use, let's say you get 2 of these, for 1 glucose you get 2 3PGs, and so you would get 2 of these. What's 2 times 2.5? What if instead of using the aspartate malate shuttle, you use the alpha glycerol phosphate shuttle? You'd get 1.5 for an FADH2 twice. So if anyone has ever seen the slop in the final balance, they normally give you a range. And when I was young, I used to go, well, why is there slop? Well, because there's variation within the cells and how they solve these problems. Then it starts to become very determinate. When you go in through PDH, remember you decarboxylate, and I think you form 2 NADHs. Oh, one for each pyruvate, of course. So that's 5. Each turn of the TCA cycle makes 9. We saw reduced these things, and you get 1 substrate level guanine diphosphate phosphorylation each turn. So if we add all this up, you get a range of 10, 7, 20, 30, I don't do math. But you get that range at the bottom. Calculators do math. Yes, sir?
Does the oxidation of mitochondrial NADH include the FADH?
Yes. Yeah, that ought to say again. You inherit these figures, and then it takes forever to get them actually accurate. It's why, by the way, it's why you can have 10 editions of your textbook. You keep finding these little things as you go along. Thank you. All right, does that all make sense so far? Okay, so let's finish off. This is interesting. I told you earlier in class, I hope I didn't make too big a show of it, but the word efficiency, almost no one in the lay world uses it properly. So we're now going to learn what efficiency would mean. So efficiency, often written with that kind of a curvy E to distinguish it from energy. Efficiency is always a ratio, and the ratio is always something like work done. So at the top is always what you're trying to accomplish over the total energy expended. And so you will learn as we go further in this class that, for instance, if you're doing 200 watts of work on a microgometer and you measure oxygen consumption to see what the stable total energy release is, 800. If you do that ratio, you get something like 25%, I'm pretty sure. And isn't that interesting? So 25% of the contractile energy released in contraction actually does the work. And the other 75% is heat. Got it? But always it's a ratio. So what I'm about to show you now is metabolic efficiency. It's a slightly different concept. This is work efficiency. This is the most technically correct way to use the term. Is a ratio of what you're trying to accomplish. Miles per hour in a car per energy cost to do it. Oh, by the way, you try in efficiency to always have the same units on both sides, so you can do this in watts and watts, and then you get a percent. So what we're about to put up here is, we just showed the breakdown of glucose. And so what were we breaking down? What were we hoping to get out of the glucose? What was the point? So ATP, energy, yield. What's the bottom part going to be? Technically, it's the enthalpy, if you want to get all physics about it. It's the enthalpy of glucose. It's how much total energy was contained in that molecule. Are you with me? So how much did we get out of the original glucose and actually make it into the ATP? Are you ready? It's not terribly impressive, but it's better than some of them. So there you go. 35% of the total energy in glucose actually gets harvested into high energy phosphate by the steps that we've talked about in the cytosol and then into the mitochondria. It's pretty impressive. It actually beats out most automobiles. And by the way, automobiles, you put fuel in them that's already been highly refined, so the energy cost in an automobile of producing the fuel has been eliminated. Here, we're including the actual cost of deriving the fuel. So this 35% apparently has another 10% step down when you take that ATP and actually release that energy through the myosin head. You get another 10% step down to wind up with a total work efficiency of 25%. But again, since we're actually synthesizing the fuel as we go along, we're rather better than automobiles. This has gone off again. Song, you got to email me the last.
Yesterday, sorry about
Please
that.
do. No, it's okay. But just for them on the weekend, of course, for your class.
Professor,
Yes, sir.
Would it be lower if you included chewing food and the different?
Yeah, it's amazing how little. Yeah, you're secreting enzymes of digestion, peptidases, and all. Certainly, that has a cost. I've never seen a complete calculation. You'd be surprised how small that is. The processing is tiny compared to the losses of the. What is the other that's not enthalpy? The entropy. The entropy losses are the worst problem. But you're quite right what you just said. It'd be fun to measure it too. I mean, if you like it. All right. So now we're in heat. Let's never say that. Let me sorry, I'm just inappropriate. Let me finish by showing you a beautiful little molecular, I believe one of the biochemistry professors shows it, maybe Dr. Brick. Has anyone seen this thing of the ATPase functioning? I think you'll see. If I can get the thing to open up and play, let's see if this is a nice way to finish. You can start to pack up, but try to be quiet. And let's see if I can make it go. Go, go!